the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are currently going through linear transformations. Prior to this specific video, you should probably have already watched or gone through or read the textbook on transformations themselves, like what they are, matrix transformations, and linear transformations. Those are going to be core to the conversation that we're going to have here. Now, from this point forward, each major section of material that I go through will end with a single video titled Synthesis Questions, because it starts right about now where you start hitting these homework problems or assignments or theory questions that are very, very bulky, I would say, something that just seems daunting. And so I pick some of those questions and I do them as examples so you can see how you attack the questions. Now, let me just say, there are dozens upon dozens of these synthesis questions that could be asked in every single section that you come across from this point forward. So there's no way that I can capture all the possible methods that you're going to use. However, the techniques that I showcase in this video and future synthesis question videos should give you the ability or the confidence to be able to tackle those problems systematically. So let's go ahead and dive into this. Suppose that we have vectors v1, v2 through vp, and they span Rn. Now, each of these pieces that you're handed are very important, so being able to dice that apart and say what that means is going to be important. But we'll keep reading and then we'll summarize when we start the problem. We're going to let T be a transformation from Rn to Rn, and it's a linear transformation. That's going to be important because, well, they told us. We're also going to suppose that the transformation acting on v sub I for these vectors right here, so the transformation acting on each of those vectors turns each of them into the zero vector for I equals 1 through p. So these vectors right here are not the zero vector originally because they span an entire space, which means that they create Rn. So they can't just all be zero. If they were, there would be no way that you could generate Rn. However, when you plug those vectors into the transformation, each of them turns into the zero vector, which is kind of weird. Basically, the transformation turns them off. So our goal is to show that T must therefore be the zero transformation. What do I mean by the zero transformation? Because that's probably new to all of us. The zero transformation is essentially the zero matrix. And I can't bold that zero. I suppose I can make it kind of bold like doing this. That is the zero matrix. It's a matrix full of zeros, that's it. And if you were to do the math on that, 0 times any vector is going to be 0. So that's our goal. We're going to use every little bit of information they've handed us. What would be very cruel is if they overhanded us information. In other words, if they handed us extraneous information that doesn't help. That would be terrible. But they're not going to do that, not in a textbook, but in real mathematics. As you step out into the real world of mathematics and have to prove things, the whole world is at your fingertips, and there's a lot of extraneous information out there. So you have to go through the noise and pick the pieces of theory that apply to the situation you're working with. Luckily, they start us with that stuff. So suppose that we have these vectors, and these vectors span Rn. What can we say about that? So first I'm going to start with that supposition, and then I'm going to talk about what that means. What does it mean for a set of vectors to span Rn? This means that if we had the set of the vectors v1 through vp, and we said the span of that would generate every single vector in Rn. That is, any vector in Rn can be written as a linear combination of these vectors. I'll make this even clearer. W is a vector in Rn implies that W can be written as a linear combination of those vectors v1 through vp, because W is in Rn and v1 through vp build Rn. So far I've pretty much squeezed every drop out of this first sentence, or at least the first part of that sentence. So we're done with that. We might have to somehow infer something from that, but we've squeezed as much as we possibly can for now. The next thing I'm going to state is that T is a linear transformation between Rn and Rn. We may or may not need this, but I'm going to go ahead and write down what it means for T to be a linear transformation. This is probably the most important property of being a linear transformation. And by the way, when I prove this is called the superposition principle for linear transformations. And when I wrote this down in the previous video, I proved it, but I didn't really talk about it. So it's probably a good idea to hop back here just to take a look at it. So this is a superposition principle for transformations, specifically linear transformations. So this is a very powerful property. It just tells us if you have a transformation of the sum of scalar multiples of vectors, you can break that into the sum of the scalar multiples of the transformations of those vectors. Now that's a mouthful, to be very honest with you, but you could see visually what's happening here. It just breaks apart. You can break things apart across addition, and you can factor out constants. And that is exactly what we used in our current problem. So we have successfully squeezed as much as we can out of that guy too. We're almost there. Well, now we're going to suppose that wherever we see a transformation of those vectors v, it just turns into 0. And that's for I equals 1 through p. So I'll go ahead and write that down. The transformation of any of those vectors v sub I being 0 for I equals 1 through p means that this transformation of the sum of the scalar multiples of the vectors, which we have just used the property that it's the sum of the scalar multiples of the transformations of those vectors. Well, all of those transformations, by what we just said, all of those are going to turn into 0 vectors. Now think of these 0 vectors as columns of a matrix. Then this is a linear combination of the columns of the 0 matrix. Let me actually write that down. And that means our matrix had to have been the 0 matrix. Remember what we wanted to show. We want to show that the transformation will take any vector we want, turn it into the 0 vector. If that's the case, we then have the 0 transformation. And that's exactly what we're getting. Now what I want to do right now is go back up and make sure that we have covered all the bases. Because I'm telling you right now, we're very, very close to being done, but I would like to describe to you as the viewer why we're almost done and how to kind of button it up, tie it up with a bow here. So going up to the top, everything that's highlighted in red, we've written down those assumptions. That's all this black ink right here. And we've used some deductive logic on them to kind of write out a few of their meanings, maybe one of the theorems associated with them, whatever it is. And our goal is to show that that transformation has to be the 0 transformation. Well, that's the key element here. To be the 0 transformation, any vector that I plug in has to map to the 0 vector. Now, if you read through what we've said, I'll go through line by line here. We have a bunch of vectors that span Rn. That means any vector in Rn can be written as a linear combination of those vectors. Well, let's go ahead and just arbitrarily take one vector from Rn. And this is the key right here. That's our arbitrary vector in Rn. That's the one that we will eventually say, hey, since that's arbitrary, we want to show that that has to turn into the 0 vector. Well, that arbitrary vector in Rn, because v1 through vp span Rn, that arbitrary vector can be written as a linear combination of v1 through vp for some scalars ci. And then we switched gears. We really didn't switch gears, but then we started using the fact that t is a linear transformation, and we forgot about the fact that this linear combination that we were using for the rest of the time represents an arbitrary vector in our domain. So let's continue reading. Since t is a linear transformation, that arbitrary vector, which is this linear combination, turns into this summation right here, which, because all those t of v's turn to 0, that arbitrary vector, which is this linear combination right here, turns into a sum of bunch of zeros, which is the 0 vector when you finish this out. Now I'm going to really put a nail in the coffin so that the reader really knows that that highlighted linear combination is where I wanted to be. Since that linear combination, which is equal to that vector w, is an arbitrary vector in Rn. It's just a random vector. We did not say it's 1, 1, 3, 8 or something like that. It's an arbitrary vector. And since that arbitrary vector mapped to 0, well then, all vectors must map to 0. All vectors in Rn must have an image of 0 under the linear transformation. Again, we kept it very arbitrary. So if you said, well, you didn't include the vector 1, 1, 5, 8, I would say, yeah, I did. Remember, every vector in Rn can be written as a linear combination of these vectors, so I could generate whatever vector you throw at me just by choosing the right combinations of these coefficients. And that's it. That's the proof of that. So this is a great entry into synthesis questions. Notice it's very systematic. What I did is sentence by sentence, going through and listing out the meaning of those phrases. These vectors span Rn. What does that mean? T is a linear transformation. What does that mean? T of v sub I is equal to 0 for all I from 1 to p. What does that mean? And then keep my eye on the prize. Look at where I want to arrive. Show that T is the 0 transformation. And if you don't know what that is, well, you could look it up. It's probably in your text. But also, you should write out a map of where you want to go. So you need to know your destination first. Be clear on that destination and then keep striving to get there. Let's try one last example. Again, a synthesis question here. Given a non-zero vector v, and that p and v are both in Rn, the line through p in the direction of v has the parametric equation x equals p plus tv. This is a lot to read through, right? Show that a linear transformation maps this line onto another line or onto a single point, a degenerate line. Okay, that's a lot to digest. I mean, I actually had to pause while reading that so that I could actually kind of breathe it in and figure it out. Now I can see why it shows this as a synthesis question, because the graphical interpretation of this is very challenging for people to understand. So I'm going to spend a few moments talking about the graphical interpretation of this. It is kind of critical. So P is what we call a particular solution. You don't really need to know that, but P is a vector. And in the text I use, and mostly in linear algebra, a lot of people represent, in fact, you always represent or try to always represent vectors as column matrices, like single columned matrices. However, every once in a while, it's advantageous to think of a vector as a point in space, and that point in space is the tip of the vector. So for example, the vector 1, 1 can be thought of like that. That's the vector, let's call it u, is 1, 1. However, some people will reference that as 1, 1. Notice the difference in the notation. The green ink is listed as an ordered pair, 1, 1. You would never put a comma in a vector. So this is just a different interpretation of sort of the point that corresponds to the vector. That's probably the easiest way of saying that. A lot of authors use this to save space when they write things down. I much prefer column vectors, but well, that's just such is life. Now, as you can see here, I actually drew just a two-dimensional system here, x1, x2, and I drew two vectors, v and p. Now, if you think about t times v is any scalar multiple of v. So I'll go ahead and showcase what that looks like. That light green line is just different multiples of the vector v. For example, if you went from the origin all the way out to possibly about here, that's twice v. So that's 2 times the vector v, and so on and so forth. Now, adding p to that, because if you look at this x vector, that is p plus that. If we're going to add the vector p to all these possible multiples of v, well, here's a single example. You have 2v That's twice the length of regular old v there. It's kind of a little bit longer, sorry about that. But anyway, there's 2v right here. And to that we'll add p. And that's that dashed line right there. So the end result, this guy right up here, is p plus 2v. And what ends up happening if you start adding up any multiple of v to p, you get this line in 2D. It is parallel to v, but it's shifted by an amount equivalent to the vector p. So essentially every point on this blue line is a point represented by p plus tv. So this point right, actually it'd probably be right here. This point right here is the vector p plus 1v. That's pretty darn close. I was just eyeballing that. The point right here is p plus 0v, and so on and so forth. Right, so all of the possible values for p plus tv is that line, that blue line right there. All right, that's the setup for this, and that's usually very challenging for students to understand. Please note the vectors p and v in the problem we're going to do are in Rn, not r squared. So that's not going to change our visual. We're just going to keep with that visual, but I'm just letting you know that we're not in r squared in this problem. So let's reread the problem. Given that v is non-zero, which it's not in our picture down there, and p and v are in Rn, which they're technically not in the picture down below, the line through p in the direction of v, and I'll highlight that here, the line through p in the direction parallel to v is really what that means, has the parametric equation x equals p plus tv. Yay. So now we have a good visual of what's going on. None of that, by the way, was anything we could really use yet. We've squeezed as much as we can out of this statement. We've drawn a picture to really help us try to understand stuff. So far we have written down on our board as much as we possibly can use there. What we want to do from that is show that a linear transformation from Rn to Rn maps this line onto another line or onto a single point. So they didn't actually hand us the transformation. So all we can do is assume that t is a linear transformation. So I'm going to say, since t is a linear transformation, I'm squeezing some more information out. And before I continue forward, I'm just going to go ahead and say, well, since t is a linear transformation, t of x, which is t of p plus tv, so I'll do that. Well, that's equal to, again, t is a linear transformation, so we can pull that apart across addition, and we can factor out any constants, and that is a non-vector, so it's going to be treated as a constant. Now, just a heads up here, t of p is just a vector, and t of v is also just a vector. Let's go ahead and just call these u. Actually, I can't use u and v because v is being used. We'll call them u and w. And by our entire conversation up above, the line through the vector p in the direction of v has the parametric equation x equals p plus tv. It's a line through p in the direction of v. If you replace those letters with, what do we have here, u and w, then we can say a line through u in the direction of w, I'm just stealing a lot of this language right here, is the parametric equation I wrote as y equals u plus tw. You don't really need the y in there, I'll just erase that. So I'm going to go ahead and make a mention right now. If w is non-zero, and that's required because if w is 0, then it's very similar to this right here where the coefficient of v is 0. So it would be this, it would just be the point p in space. So if w is 0, not 0, sorry, if w is not 0, this is a line through u in the direction of w. If on the other hand, w is actually 0, that is, the transformation of v is 0, then this is a point. This is just a point u, and that is just because, well, w is 0, so it would just be this vector u, which is just a constant, so it's a point. Now this type of problem, by the way, we are done with because we have now shown that the linear transformation t maps that original vector x, which is p plus tv, onto another line, or perhaps onto a single point, that is if t of v is 0. So we have successfully finished this problem, but I do want to mention that this level of complexity, man, it is a lot for students to digest, especially the graphical problems. That's why I wanted to do this one. Just note, keep this image in your brain, that a constant vector plus a variable times v leads to a shifted blue line that's parallel to v. It's shifted by the vector p. All right, I know that still sounds confusing. It sounds confusing in my own head. So anyhow, I hope that this was somewhat helpful. Just remember, when you're going through these synthesis style problems, take your time, write down everything you know from the information they're giving you, and work with fellow students. That's critical. Help each other out. Find the person who gets it and ask them, hey, what am I missing here? And they'd be able to describe it to you maybe in a better way than your professor can. Anyhow, I hope this video helps, and I hope you have a wonderful day. Be just an excellent human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.